Okay, I'm going to share my screen. This is the last, the last thing we saw last class was this graph where we show a time series that is stationary. So now let's talk more about this issue of stationarity and so on. We saw that in the case where we assume that the weights, the sum of the weights of psi1, psi2, and so on converge, then neither the mean nor the variance and covariances depend on time. Okay, that's what we would call a second-order stationary process. So if the mean doesn't depend on time and the variance covariance structure does not depend on time, then we say that we have second-order stationarity. Okay, and we're going to be looking for to have at least a second-order stationarity to be able to model the time series that we will find in practice. Now, a stochastic process will be strictly stationary if I can take an arbitrary set of variables, the z time t, t plus 1, t plus m. It doesn't matter what time t is. I take the m consecutive measurements, and if I change the origin, the joint density function of both sets is the same. So if that happened, then we have strict stationarity. That is, the process will be strictly stationary if the joint distribution of any subset of information is independent of time. Okay, so I have this doesn't depend on the time t that I start with. Here I'm starting at time t. Here I'm starting at time t plus k, but the joint density is exactly the same. That's strict stationarity. That's very difficult to show. That's very difficult to assess. But so we'll be happy to have the second-order stationarity, and that's it. But definitely, if a process is strictly stationary, then it will be second-order stationary and first-order stationary. Okay, because the mean and the variance covariance structure is not going to depend on time. If the two functions, the joint densities do not depend on time, then their moments will not depend on time. Okay. From this expression, when we have the two joint densities, if the first two moments exist, then the expected value of zt and the expected value of ct plus m will be a constant that doesn't depend on time. The variance of zt will be the same as the variance of ct plus m. We'll be calling this thing gamma null. And the covariance between ct and ct plus k will be the same as the covariance of ct plus m and ct plus m plus k. That is, the covariance between a couple of elements in that series, which is the realization of a stochastic process. That covariance will only depend on the separation between the data. Okay, if you here the separation between ct and ct plus k is k. Here the separation between the separation in time between ct plus m and ct plus m plus k is k. Okay, and it's gamma k. That's the covariance. K lags ahead. K lags ahead or behind. Okay, it doesn't matter if it goes ahead of time or we go back in time. The covariance gamma sub k, which represents the covariance k lags apart. K lags. We'll call this thing that these periods of time we'll call them lags. So this will be k lags apart. That's all that matters for the covariance, is how far away the observations are. Okay, strict stationarity, therefore, implies second-order stationarity. Because if these two density functions are the same, then this thing holds, and then we have what we call second-order stationarity. Okay. The reverse is not true. Okay, if I have second order stationarity, then that does not imply necessarily that I have strict stationarity. The only exception to that is when the joint distribution is multivariate normal. Okay, if the joint distribution of these variables is multivariate normal, then if I have second order stationarity, that means that I have strict stationarity. But again, that's the only case where that happens. But since we're going to be assuming that the random error, the random component in the time series that we'll be analyzing will have normal distributions, then it's we only check for second order stationarity. Checking for strict stationarity would be very, very complicated, and it wouldn't be worthwhile. Okay. This is what I just saw. So it will suffice that the mean invariance covariance structure that does not depend on time, to assume that we have stationarity, the type of stationarity that we need to model the series. Now, to avoid, the covariance depends on the units of measurement. So to avoid the influence of the measurement units, what we normally do is work with the autocorrelations. Okay, just like in the one-dimensional case, the covariance doesn't really say much. We don't know if our covariance is too high or too low because it depends on the units of measurement. So to avoid that, we are going to be working with the correlations, which we call now autocorrelations, because we'll be measuring the correlation of a random variable with itself x k periods ahead or k periods behind. So we'll call that rho sub k. That's the autocorrelation at lag k. So the lag k autocorrelation, rho sub k, is just the covariance divided by the variance. Okay, is the covariance divided by the variance. So it's going to be gamma sub k divided by gamma null, which was the variance, and that will be for k equals 0 plus or minus 1 plus or minus 2 and so on. This function is symmetric around 0, right? So we have the covariance k periods ahead, the correlation k periods ahead will be the same as the correlation k periods behind. So we have this, that's how we calculate these autocorrelations. Given that we have a finite realization of the process, we do not have these numbers, these autocorrelations, we do not know them, but we estimate them based on the data that we have. Now, to be able to estimate these autocorrelations, we need to assume that the stationary process has a certain ergodic properties that allow the equivalence between expected values and sample estimates. These ergodic properties, essentially what they mean is that the process is essentially the same regardless of where you are in time. Okay, that's essentially what these ergodic properties say. If that happens, then the sample estimates will be will approximate for large n the true values of their autocorrelations rho sub k. The autocorrelation matrix is this is an autocorrelation matrix of a stationary process, and again it's symmetric around 0. The autocorrelation one lag ahead is the same as the autocorrelation one lag behind, and the same thing for 2 lags, for 3 lags, for 4 lags, and so on. Okay, this goes on forever, let's say. So the autocorrelation matrix will have always a 1 in the diagonal, because the autocorrelation of a variable with itself at the same time is going to be 1. And then, for example, here, this is 0.8. That means that the autocorrelation between CT and ZT minus 1 is 0.8, but that's also the autocorrelation between CT and CT plus 1. In this, the 0.4 will be the autocorrelation between ZT and CT plus 2, or CT and CT. Pardon me?
Sí, me aparece en el sistema. ¿Por qué?
Pues porque son 19,000 pesos de colegiatura.
here. I cannot mute Victor, and I guess I don't know if anybody else is with the mic open. Okay, so that, and we're going to be dealing with autocorrelations because that then we know that they are always bounded. They are between -1 and 1. Okay, and the closer they are to 1 in absolute value, the stronger the relationship it is. So, for example, here we see that the ZT is strongly correlated with ZT -1 and CT +1. But it's not, it's very weakly correlated with CT and ZT -3, for example, right? Or CT +3. Now, from these ergodic properties that I mentioned, we can estimate the process mean as the average, the sample mean of the observations that we have, the series that we're observing. Of course, we are assuming here that the mean is finite, okay? And for the mean is the mean is finite, and not only that, we also assume that the limit when n goes to infinity of this sum of the autocorrelations is going to be equal to 0. That is that these autocorrelations will tend to 0, okay? There will be a point in time when they're essentially undistinguishable from 0. The same manner that we assume that the mean is finite and we have this condition hold, then if gamma k, if the kth autocovariance is finite, then we can estimate the lag k autocovariance as, well, I'm calling this, instead of gamma is the population parameter, the autocovariance in the population, and the estimate from the sample, we'll call it here Z sub k, and that's the average of over from t equals 1 to n minus k for any value of k of ZT minus Z bar. I just subtract the sample mean times CT plus k minus Z bar. Okay, for k equals 0, 1, 2, and so on. So that's the sample estimate of the covariance. And then the sample estimate of the autocorrelation. The sample estimate of the autocorrelation will be the sample autocorrelation. And this is the formula of the correlation between two variables, but now it's the same variable, except that it's lagged k periods ahead or k periods behind. Okay, but that's why we call it autocorrelation, because it's essentially the correlation between the variable ZT and the same variable, but k periods apart. Okay, this will be the estimate of the autocorrelations, of the sample autocorrelations, of the population autocorrelations. So we'll take a look at a purely random process. Let's take white noise, A sub I, which is normal, a normal random variable with mean 0 and variance sigma squared, and they're independent, so their covariances of the covariance of AT and AT plus K is going to be 0 because they are independent and they are normally distributed. If you graph this series, if you make a plot of this series, it will look something like this. So it will fluctuate around the mean level. And if you look at the autocorrelations, the autocorrelation at lag 0, it's always 1. That's not surprising. But these bands here, we'll see later how these bands are computed. But these bands that you see here in dotted the blue lines represent confidence interval, let's say, that's built assuming that the correlation, the real autocorrelation is equal to 0. So if we assume that the autocorrelation at lag 1 is 0, then this will be a confidence interval for the sample that we get from the sample autocorrelations. Okay, so anything that lies between these two lines is considered white noise. It's considered noise. It's not significant. So you see here that when we have a random process which is white noise, then the autocorrelations are all zero. The autocorrelations, I don't count the first one because it's always one. Okay, so all autocorrelations, lag 1, lag 2, lag 3, and so on, are going to be equal to 0. Since the autocorrelation function is symmetric around 0, we always show only the autocorrelations to the right of 0, like 1, 2, 3, and so on. Now let's take a random walk. A random walk, if A sub t is mutually independent with mean mu and variance sigma squared, okay, particular case would be when the mean is 0. ZT, a process called ZT, will be a random walk if ZT is actually CT minus 1. So if CT is the observation at time t minus 1 plus white noise plus A sub t, a random variable, and that here we're assuming that has mean mu. So the expected value of ZT will be t times mu. Okay. So what this is telling me is that the expected value of CT depends on T, right? The expected value of ZT depends on T. And the variance of CT is T times sigma squared. See? So the expected value of CT, look at this thing. Let me, here, expected value of CT is expected value of CT minus 1 plus AT. Okay. Now, expected value of CT minus 1, that'll be expected value of, you can compute this thing as expected value of ZT minus 2 minus AT minus 1 plus AT and so on. You could be developing this thing that will be T times mu, the expected value. And the variance is just going to be T sigma squared, because the variance of CT is the expected value. The variance is expected value of CT minus its mean, and its mean is T mu. Okay. And that's going to give you T times sigma squared. So both the mean and the variance depend on T, on the time. So this is a random walk, is not a stationary process. It's not a stationary process. If we now take the difference between CT and CT minus 1, that difference is AT, and that's a pure random process, and therefore is stationary. Okay, a pure random process is always stationary. This is the plot of the first difference of ZT and CT minus 1. And you can see the differences here between the autocorrelation functions. The autocorrelation function of a random walk doesn't die fast, quickly to 0. Okay, so this thing is not converging. The rows of case do not converge to 0. And this, in fact, and in the case of the difference, which is a stationary process, we have the autocorrelations equal essentially to 0, because all of them fall between these two limits. Okay, so we have cases here where the process itself is not stationary. If we take a difference, we're making it stationary, because now it fluctuates around a constant value, and its autocorrelation function dies to 0 very fast. Yeah, it's actually 0 right away. We'll see another example. This is a chemical process of, is a yield of a chemical process. This example, I took it from the book of Box and Jenkins, which is now has now more authors. It's Box, Jenkins, Reinsel, and Young. But there's plenty of examples there. This is a chemical process example, And you see the time series here. And this is the autocorrelation function. One of the things that you can observe here is that series fluctuates around a constant value. Okay, it fluctuates around that. And the other thing you can see here is that the autocorrelation also dies very fast. See, I only have the first and the second autocorrelations, row 1 and row 2, which are different from 0. The rest are statistically indistinguishable from 0. Okay. So I have my autocorrelation function dies very fast. So this process seems to be stationary. Okay. Now let's look at the autocorrelation function of another series. Let's look at the consumer price index for Mexico from January 1982 through November 2016. And this is the graph of the series. As you can see, there's clearly a trend in this series. And if we compute the autocorrelation function for the series, then it doesn't die fast to 0, doesn't die quickly to 0. It dies very slowly to 0. It tends very slowly to 0. It will not converge until very far away in the time to very small values. And that, therefore, this series, it's, although we can see it from here, from this graph, it's not stationary because the mean depends on the time, right? The mean depends on time. But that's confirmed by the autocorrelation function. We'll see that the autocorrelation function for a series that's stationary will decrease very rapidly to 0. I'm going to move to a script now. Let's see. You have this script in Brightspace. It's called ST02 Foundations. If you can download your script, and you're going to need the data that's in the yield batch chemical process, B&J. It's an Excel file, which you have in your data section in Brightspace, and the inflation file, the Inflación Mexico 1982-2016, which is also an Excel file, and you also have it in Brightspace. So download those two files to your computer, and also the script, and we'll execute the script now. Download, and once you download the script, just run all the lines until you set your working directory to wherever you have your data. Okay. And we'll start then generating the pure random process and see how it looks. Okay, you're all set?
What was the data we have to download?
There's two files. One, we used it last time, I believe. One is the Inflación Mexico, 1982 to 2016. And the other one is yields batch chemical process, BNJ, and that those both are Excel files.
Cool. Thank you.
Okay, they are. Wrong side here. That is the info. See that this is a chemical process temperature. There's two versions, one in Minitab and the other one that you download the other one, which is an Excel file. And there is the Inflación Mexico. Let's see how we call it here. I think it's the name is different from the one I have in my directory, but this is Inflación. It's called Inflación Mexico. No, this gives you this is the Excel file we saw last time. Let's see. Oh, here it is. No, it's not. Unfortunately, I haven't found a way to order files alphabetically in Brightspace. Let me put my file exactly the way I have it here in Brightspace, and that'll be the last file. That'll be easier to find if it's the last file here. Data sets, time series. Inflación Mexico. Okay, cálculo. Let me look at the properties. Let me make sure this is the XLX file. Yeah, that's the Excel. I'm gonna put this file in Brightspace, and it'll be the last file in the data. Well, I'll put it here, right here. It's the last file here, okay? Inflación Mexico 1982 to 2016. Okay, have you all found download your script and the data sets? So I already ran up to. Pardon me, Marianne?
I already have the
You already? Okay.
files and the script.
Okay, good. Let's so I ran up to line 19, so I loaded the packages, and let's first generate a pure random process. So I'm going to use this function rnorm, which generates random numbers from a normal distribution with mean 0 and variance 1. Okay, so it's a normal distribution with means, and I'm going to generate 500 data points. So I set the seed 1, 2, 3. You may get slightly different numbers because these are random numbers, and although you may set the same seed that I'm using, the seed serves in this. If I do it again in the same computer and I use the same seed, I'll get the same numbers. But if you're wearing different computers, you will get different numbers because there's other characteristics that they consider, like the speed of the processor and things like that, and the internal date and time, which may be different from the computers and mine. So I generate this Z norm. I put in Z all these random numbers. I have and I'm gonna do a plot of Z. And I'm going to plot the autocorrelation function of that series. I'm going to do the two plots in one frame, in this panel here on the right, the upper right on my screen. So to arrange the two plots in two columns and one row, I use this function. Par is a function that's used by the graphics commands in R. It's different with ggplot. Different to do this thing in ggplot is different, but with the simple plotting function in R, it's par, which is parameters for the graphics that I'm going to generate, and I'm specifying here that I want a matrix with 2 rows and 1 column, and I'm setting the margins. It doesn't matter with the margins. You can do it without setting the margins. And I'm going to plot Z, and that's the time series that I generated. Put the title in, and I generate the autocorrelation function. That there's one function that's called ACF. We'll be using another function later, which is from another package. But for now, we will be using the default autocorrelation function that comes with R. So I'm computing the autocorrelation function. This is a graph that I have in the presentation. Essentially, the series fluctuates around the mean level, and the autocorrelations are on 0. That is the random. That's a random walk. That is a purely random process. Okay. Now I'll generate the random walk, and for the random walk, I'm going to generate 1,000 numbers with mean 0 and variance 1 from a normal distribution. And then I'm going to do a cumulative sum. And remember that for the random walk, CT is equal to CT minus 1 plus AT. So it's always the previous observation plus random walk. So I achieve that by just computing the cumulative sum of Z. So X dot RW, which is for random walk, will now have the random walk. If I let me look here at I'm going to say the head. Let's see, C bind, C, X dot RW. And these are the first 10 numbers. We control enter. So this is what Z has, and these are the numbers that I generated, and this is the random walk. So this number will be the previous number, okay, plus the random error, the Z random variable. Okay. And I get this random walk. If you plot it now, I'm going to do the same setting, 2 graphs in 2 rows, two rows, 1 column, and I'll plot the random walk. As you can see, the random walk starts. I'm going to do the whole charts here. I plot the random walk, and then I plotted the correlation function, the autocorrelation function. You see, the random walk starts moving around. Actually, for this random walk, we generated the numbers with mean 0, right? With mean equal to 0. But the variance is increasing with time in the random walk. Okay. As we saw here, let me go back to this. Oh, no, I closed the presentation already, but remember that the variance was equal to sigma square times c times the time. So as time increases, the variance starts increasing, and this thing is fluctuating. It will come back eventually. It will come back to 0 because I generated them from 0 being random variables. But you can look here at the autocorrelation function, and the autocorrelation function is really dying very, very slowly. Okay, it's dying very, very slowly. That's a clear indication that we do not have stationarity. You can see here that this thing is the slope at which this thing is decreasing is very, very small. Okay, so we do not have stationarity here. But if I take the difference of this random walk, I'll take the difference now. I'll close this. I'm going to take the first difference. I'm going to say x dot RW is the QSUM. I already have that. I did that here up here. So I'm gonna do erase this line because I already computed that earlier. And I'm gonna plot the difference. There's a function called diff. If you look at diff here, let's take help diff. This function computes a difference of a time series. So we'll use this lag time series differences from the base package. So there's one, the first parameter here is the series. Then lag by default is equal to 1. That is, lag means if I'm going to look one lag behind, or if I set lag equal to 2, that will be 2 lags behind, and so on. And differences is the coefficient of the inverted delta operator, the difference operator. So if I take delta and inverse difference squared, that will be difference is equal to 2, okay? And lag equal to 1. So the function diff computes the difference. So I'm going to plot the difference of x.w RW, and then I'm going to plot the ACF of this difference. Okay. I'm going to plot this, the title, and this is the ACF. So as you can see, the difference now fluctuates around center, some constant value, and the autocorrelation functions are, the autocorrelation function is essentially 0, except for 1 for the autocorrelation that lags 0, which is always 1. So they die right away, these autocorrelations. So the process, the difference between CT and CT minus 1 is a stationary process. Now let's look at the chemical process yield from Boxer and Jenkins.
Teacher,
Yes.
I think our script isn't complete. Well, I only have until first difference of a random walk.
Oh, really?
Yeah, me
Yeah.
too.
Okay.
Yes, and I think we have many lines different from yours.
Yes, even the library, it's not the same.
Let's see.
Ours is even in Spanish.
Yeah, it's in Spanish. I started translating the scripts, but I'm gonna give up. It's not. It doesn't make sense to translate all the scripts that I have. So I started doing that. Let me see. Servicio tiempo. No, this is data sets. I'll put it in. I'll load it. You don't have to rerun the libraries and all that sort of thing because that's you already loaded the packages. Our scripts, and this is SD02 foundations. Now it's going to be the last one, okay? SD02 foundations. Okay. You let me know when you're ready. Yeah, and the one you had, well, you didn't have the reading the chemical process yield. in your script that I had before?
No,
No,
it
okay.
until the 39.
It ended here,
Uh-huh.
actually. Okay. Well, yeah, you've downloaded this script already? Are you set?
I'm working on that.
Okay.
Sí, así es. Me lo dio y pues, o sea, viene de esto. De acá.
Okay, I muted everybody because there was some.
Professor,
Yeah.
I have a problem with my R.
What's happening?
Every time that I try to execute a command, it doesn't do anything.
Okay, let me stop
Um,
sharing. Can you share your screen,
Yes.
please? Hold on, let me allow you to. That's it. Yeah, you can share now.
Here. Every time I try to execute, it puts me on this in this part in terminal.
Go
but
to the
only
console.
thing is here.
There's all the results are going to be shown there in the console.
Yes, but every time that I try to read a line of work, let me show you.
Okay.
It goes there.
You tried. You typed what? If required time series. You typed what? Control Enter.
Control Alt Enter.
Oh no, it's Control Enter only. Control.
Okay. Sorry.
Okay.
Thanks.
And then you have to do the Control Enter to the other line.
Yes.
Okay.
Thank you.
Okay, now I guess you'll have the script now. So I'm going to read the chemical process data. What we have is just one single column, which is the yield, the chemical process yield. I'm going to convert now. I'm going to use this function TS to convert that to a time series object. TS is a standard function with R. Later we'll see that for some series, it's better to use a different structure, which we'll be discussing next time, which is the zoo structure, ZO like zoológico. That structure gives us more flexibility. With this TS structure, we have enough to handle monthly data and we can have, let's say, even not monthly, or we have daily data. That starts getting complicated with the TS structure, and we'll use the zoo structure. And when we have to aggregate data, that the other structure will be more useful. We'll look into that thing later. So I'm going to convert this thing to a time series, and I'm going to say yield equal the function TS applied to chemical process. That's a structure that I have, and the column is rendimiento. Right? I'm going to call yield is a time series of convert to time series the column called rendimiento from the file, from the data frame that I read, chem.pros.
Teacher,
Yes.
the file that it's on Brightspace, it's .mtw. So we can
there's.
read it.
Did I put the wrong one? I thought I had loaded the correct one. Let's see. It's gonna be the last one.
It's
No, it's the chemical
batch.
yield one.
The last one that I loaded is the Excel file.
No, the yield.
That one is for inflation.
Oh, the yield? Oh, okay. There's the yield. That's also an Excel file. Let's see. I have to erase this many tab files. Yield. Chemical process. Oh, this is chemical process.
It's almost at the
Temperature.
end.
It's a mini file, a mini tab file.
It's a mini tab file.
Yeah, a little more.
Okay. Chemical yield process. Let me look again at the data. Oh no, it's chemical. It's called chemical process, right? Chemical yield, chemical process, chemical. Let me remember the name here. It's
I think it's yield batch.
yield.
chemical
It's yield.
process.
I was looking for chemical, but it's yield. It's yield.
There at the end.
There it is. This is the Excel file. I loaded the wrong file.
Thank you.
So it's going to again show at the end. That's it. Okay. Now it should be there. Okay, we're all set.
Yes.
So I'm going to make it a time series structure. If I look now at structure of yield, it will just tell me that it's a time series. Okay, it's a time series. So if I do a plot now, here, remember earlier what I had to do is plot the X lab, I put time, and then in Y lab, I put the data, right? And use a type equal L in the plot. Now, since the plot recognizes that this is a time series, it will just plot over as we will assume that it will plot the series in the order in which it is set up in this vector. So if I got the say plot yield, that's the yield for that time series. If you look at the TS structure, help, I'm going to say help TS. And it tells me here what the data is. By default, it starts at 1. Okay, it starts at 1, and by default, frequency is equal to 1. This is this process. This data is actually an hourly data. So it doesn't matter here because with TS we cannot handle hourly data the way we can handle it with a SU object. But we'll be using this thing here. If the defaults, if I have monthly data, for example, then I would use frequency equal 12, because what that frequency specifies is how many observations per time period. So if monthly data, if I have my time period will be a year, I have 12 observations per year. Okay. For daily data, I cannot use the frequency equal and the 52 because the year doesn't have exactly 52 weeks. But for this particular series, it will suffice to do the same. When we'll see later that I can specify a time to start the series. For example, for monthly data, I can specify a year and a month. Okay, and it'll be a combination of two. It will be a vector that has a year and a month, but we'll see that later with the inflation. Now the plot, that's a plot of yield, and as you can see that it fluctuates around the center level, constant level, and I'm going to do the ACF of the yield, and that's the graph that you have in your presentation. You see that the autocorrelations are essentially zero after lag 2. It's lag 1, lag 2, and the rest are zero. You always, if you use the ACF function, you always ignore the first one because it's always 1. We'll be using another function, which is part of another package that starts at 1, and that we'll pay attention then from the first lag. But here the first lag is 0, and we ignore that. It's essentially 0. So this is a stationary series. The autocorrelation function is dying very fast after it essentially dies after the second spike, the second lag. Okay. Now let's look at the inflation, and that's Mexico CPI from January 1982 through November 2016. I'm going to read the file, and if you see what it has 2 columns. It has a date column, which is called fecha, and the IPC general, which is the índice de precio al consumidor general for Mexico in that period of time. It starts in January of 1992. So when I convert this to a time series object, I'm going to call that CPI. I'm going to use the same name I have here. I will no longer use this data frame. So I'll just keep the time series object. CPI is TS as a function, and it will convert this column, the IPC general, to a time series that starts on the January of 1982. So I can specify a year and a month that the series start. I do not have to specify the end. I know the end in this case, so I'll put it there, but I do not have to specify the end. It will determine what the end is depending on the number of data points that we have. And if you see here, I'm using frequency equal 12 because I have 12 months in a year. So I convert this to a time series object. I'm gonna plot again the series and the autocorrelation function. That's the time series and the autocorrelation function. I can do it the other way around. I can do parent row 2, 1. I think it looks better. 1. Run. So this way it looks better. I'd say this is a time series. There's a trend, definite trend, so that the series depends on time. The level of the series is changing with time, and the autocorrelation function doesn't die to 0. Okay, it's very, very slow. So this series is not stationary. Okay, so now we have, let's take a difference of the series, and I'm gonna remove this comment here. I'll leave it as 2 rows and 1 column. Okay, I'll do this thing. I'm going to compute the first difference. I'm going to call it D1 of CPI. The first difference of CPI is the difference of CPI. Remember by default, the lags that it's going to difference is 1. So that's the first difference of CPI. I plot now the first difference, and I plot the autocorrelation function of the first difference. Here, you can see in this autocorrelation function, something that we're going to be studying later, that's the sort of behavior that it can have. The autocorrelation function is not dying very fast. It's not dying very fast. And in fact, if you look at this type of behavior, you see it apparently dies here, but then it starts growing again. So yeah, I have a pattern that grows, decreases, is practically zero, and then grows again. This already is telling us that we may have a seasonal behavior, because the ACF is not really dying very fast. I can draw a line here. I can draw a line to see how fast this thing is growing, is dying, and it's not dying very fast. You see, it goes like that. It's not dying fast. This is very high also. Oh, I'm sorry. I took the one, the aerial drawings. I'm sorry about that. I forgot to skip the one. See the slope that autocorrelation function is dying is very small slope. That's very low decay in the autocorrelations. That means that this first difference is still not stationary. It's not stationary, and it's not stationary for a couple of reasons. One of the reasons that you can view from the graph of the first series that was not so evident in the graph of the series or the original series is that the variance is changing. Look at the, I'm going to draw the lines also here. Look at the spread that I have in this section of the series. And then look at the spread that I have in this section of the series. And look at the last section of the series. If I look at variability. So the variability is also depending on time. At least it appears to be dependent on time also, the variability. So the first difference may not be what we need here to make it stationary. I'm going to try now something else, and that's part of what we will be doing when we are trying to identify a model. And I'm going to compute a second difference. Okay, I'm going to eliminate this thing. And I'm going to compute the second difference of CPI. And I can compute it two ways. I can compute the second difference by taking the first difference of the first difference. Okay, it's a difference of the first difference. That's one way of doing it. And I'm computing the second difference like that. The other way I can do it is I can say, let's say, let me do a head here. Head D2 CPI on 10. There's the first 10 values. And I can also do it as second difference of CPI equal div D1 CPI differences equal to. I want the second difference of, I'm sorry, but this had to be the original series, the CPI. Okay. I'm going to put that thing in the script. Copy. I'm going to put it here. And I'm going to do head D2 CPI on 10. Okay. So I get the same values.
I'm sorry. Why are we using the difference of the difference?
We can do either. We can do the difference of the first difference, or we can do the second difference. Okay, the power 2 of differences of the original series. These two things are equivalent. Okay. One mistake that often is done when using this difference function is if I compute it here instead, let me see head. If I take div the CPI, comma 2, because there's a lag parameter in the difference function. Okay, this thing is a completely different thing. This is not what we want. This gives us a completely different value. Okay, so the right way to compute the second difference is either by computing the first difference of the first difference, okay, the difference of the first difference, or using the parameter differences equal to 2. Okay.
Okay,
So
thank you.
this is Let's see. So here, this is the second difference of CT, and this is also the second difference of the original series, right? You can use either one. Now I'm going to plot the second difference, and it's ACF, it's autocorrelation function. You look at this autocorrelation function, one of the things that you see is now the autocorrelation function is still not dying very fast. Okay, it's not dying very fast, but there's a clear pattern. There's something going on at month 6 and at month 12. This is 18. This is 24. So I have definitely have a seasonal behavior, which we could see since the previous plot. Then the other thing that we observe is the change in variance. It's this in this graph is very clear, the change in variance. We have very small variance in this section. It increases a little bit here, and it increases even furthermore by the end of the time series. Now, we will not fix this part, this type of behavior. We will not fix it by taking differences. We'll fix this thing by taking transformations, by making transformations. But this tells us that we have a stationary pattern. And we could see that from the beginning, from the previous plot, we could see that. We were seeing that something is happening here at month 12 and at month 24. Okay. So when we start looking at model identification, we'll start studying these type of patterns to be able to determine which type of model we're going to fit to a time series. Okay. Now here I'm going to show you the difference between. I'm going to take CPI. I'm going to make this a little wider, and I'm going to take CPI, list CPI, the first difference CPI, second difference of CPI, which I already computed, which is well, this is I'm going to put it like this, and I'm going to also use the one that I told you that doesn't give you the second difference, which is CPI 12. Okay, we have, and you can see this is the original series. This is the first difference, which is, for example, this minus this is 0.0449. This is the second difference, and this is the second difference. So this is I could remember that the second difference of CT is 1 minus b squared. 1 minus b squared applied to CT. So remember, it was 1 minus 2b plus b squared CT. And that's essentially ZT minus 2 times CT minus 1 plus CT minus 2. Okay, that's what the second difference is. If you see this number here, the second difference, if you take CT is what? CT is this one here. Minus CT minus 1. This is CT minus 1. Oh, no, minus 2 times, right? Minus 2 times, minus 2 times CT minus 1 plus CT minus 2. Okay. That's 0.0001529, which is this thing here. It's rounded up to 29. So this is the second difference, which we obtained by either the first way, which is taking the difference of the first difference, or by using the parameter differences equals to in the difference equation. These two are exactly the same. If you do different CPI and just say 2 for the in the function, it doesn't take the second difference. What this thing is doing is computing. This thing is computing this. Copy. Minus CT minus 2, which will be this one here. Okay, that is computing the difference between this and this. So the 2 in the diff in the function diff. I have it here in the help. I had it here. Diff. There's a lag. This is specifying how many lags should I take apart to compute the difference. Whereas differences tells me the coefficient, the exponent of the delta operator. Of the operator, the differences equal to k corresponds to this, to applying the k power of the difference operator. Okay, and I clarify that thing because it's very common that to people to just assume that that's going to be the differences and use that as a second difference, and it's not. Okay. So let's save here and go back to my presentation. Okay. Now we're going to we're going to talk more about differences and stationarity. Because the way we're going to achieve stationarity in processes is through differencing. Most of the series that we analyze in practice are not, this is a different presentation, okay? This is the ST03 presentation, which is already in Brightspace. Okay. Now, let's talk about non-stationarity. The type of non-stationarity that we're going to be dealing with here is, well, there's two types, essentially two types. We have that we're going to be dealing in the class. One is when the variance changes with time, and we'll deal with that through transformations using the Box-Hawkes family of transformations. And the other case is where you have non-stationarity due to a polynomial adaptive trend, which is the most common type of non-stationarity besides the non-constant variance non-stationarity. When we have an adaptive polynomial trend in our time series, what that means is that I normally have something that could be maybe the slope of if I look at this series here, for example, I have 3 sections. In this section, I have it has a trend. It's growing, and it's a trend. The larger the time, the higher the value of the time series. But the slope at which is changing is touching the y-axis around this level. Okay. Now it moves. It shifts upward, the series shifts upward. It still have a linear trend. It still has a linear trend, but now this linear trend is moving. It's not where the first linear trend was, which is this. I'm going to use 1 for the first linear trend. I have 1 here, and the second linear trend is this one here. So I still have a linear trend, but it's shifted. And the third linear trend is this one here, third. So my third linear trend is shifting. So I have my polynomial trend is linear, is a linear polynomial, but it's shifting. And it definitely indicates that there's a dependence on time for the time series. So it's not stationary. It's not first order stationary, definitely. Now, the second example I have a quadratic type trend in each section of this series. So I have a second order polynomial that is showing how this thing is behaving. This is maybe closer to a straight line, but anyway, okay. So I have this polynomial trend. This is a second order polynomial trend, which indicates that the series is not stationary because it is dependent. The behavior depends on time. Okay. So this type of stationarity will be dealing with this type of stationarity, whether it is linear stationarity or quadratic polynomial trend, whether it's a linear adaptive polynomial trend or quadratic or cubic, whatever, we'll be dealing with those types of behaviors through differences. Okay, that's how we're going to be dealing with this type of behavior. Let's see. Now, this type of trend, then we'll be able to eliminate it with the appropriate number of differences. Okay, how many differences should we take? We'll determine that by two tools that we have. One is looking at the first difference of the series and the second difference of the series. Plot the first difference and the second difference. But the other one, which is a very useful tool, is the autocorrelation function. If the autocorrelation function does not die fast, that means that we do not have stationary series yet. Okay, we'll start next class here, so that we see how these different trends behave and why differencing works. Okay, we'll start next class, because it's already 11:15, and I need to give you some break so that you can be alive for your next class. Are there any questions, comments? Again, my request, if you can open your cameras, I would appreciate that. That would be very helpful to see you at least a few minutes before the end of the class. Any questions so far?
No, everything okay, bro.
Everything's okay? Okay, for next class, I'm going to ask you to, before the class starts, I'm going to ask you to download to your computer the script. It's a script called ST03. I'm going to put them in the chat. Aggregate monthly sales and all the scripts that have an _03, download those scripts. Okay, all the scripts that you find with ST_03, we'll go over those scripts, and so that you have the scripts already there. Check which files are required and download the files. And if you find a file that's not there, please let me know. Send me a mail or a message or whatever, and let me know that, so that I can put it upload the file. Okay, in Brightspace. But all should be there. In theory, all of them should be there. They were in the master. So, okay, guys, enjoy your weekend. Have fun, and I'll see you next Thursday.
Thanks, Professor.
Thank you.
Have a nice
Bye.
weekend.
Bye.
Thank you.
Thank you.
Thank
For
you,
your
teacher.
patience.
Bye.
Have
Have a
fun.
nice weekend.
Bye bye, you too.
Thank you.
Bye.